So now in this lecture I am going to talk about Galilean transformation, and these Galilean transformation leads to the special theory of relativity and Lorentz transformations. And this help us, means the Lorentz transformation, or I can say that the special theory of relativity will club mechanics and what we call electricity and magnetism, right? So first of all, let us start with the Galilean transformation and how there are some drawbacks in Galilean transformation and which leads to the Lorentz transformation and special theory of relativity. So let us talk about Galilean transformation first of all. I am talking about Galilean transformations very briefly. So consider a coordinate system. And there is another coordinate system. It's a moving frame of reference. And say there is some observation point here, it's located, and say the coordinate of this point, as you observed from this frame of reference, this is the one frame of reference, and let me call it as S frame of reference, and its position vector will be this one if it is viewed from this moving frame of reference. First of all, let me assume that this is a one frame, S frame, and let me call it as S prime frame, and this frame is moving with some velocity with respect to with the uniform velocity with respect to S frame, and say this is the position vector which is describing this. So it's moving with velocity v. So in time t it reaches at this point and say it is the position vector of this particle, some observation point as observed from S frame, and its position vector will be r prime as observed. So according to Galilean transformation, the relationship between this position vector with respect to this can be written as r prime must be equal to r vector. Let me call that it is moving with velocity u, so it is ut. So this is one equation. Now if I take derivative and here use a constant, means the S prime frame is moving with the constant velocity, that's what I am assuming. And if I take its derivative with respect to time, then it is r dot prime must be equal to r dot minus u, or I can say that it is v prime v prime, or the v velocity, it's a prime and it is v and it is u. So this is equation number 2, and if I take its derivative again with respect to time, means I am taking derivative with respect to time, and here I am again taking derivative with respect to time, then things will happen like this: r double dot prime must be equal to r double dot. So according to Newtonian mechanics, acceleration will not change as seen from one frame of reference and another frame of reference, but velocity will change, as clear from this equation number 2. So velocity will change. So that means if we are observing some light from these two different frame of reference, then the speed of light must be different according to Galilean transformation. But this is not happening in reality, because as suggested by Maxwell equations of electrodynamics, that speed of light will remain the constant always. But here what we are observing that this will remain the same. And also these three equations are also known as Galilean transformation. Most of the text people talk about that this is the Galilean transformation. But if we take its derivative, then these can be considered as the Galilean transformation for velocity and as well as for the acceleration. So what we are concluding, that means if we are observing the light under Galilean transformation, then the speed of light seems to be different. That means what we are concluding, if we observe light from two different frame of references, it will be different. It will be different according to Galilean transformation. Right? So to check that whether this is happening or not, a series of experiments will be performed to validate this observation. A series of experiments will be performed. And what are those series of experiments? Or one of the most important such experiment is the Michelson-Morley experiment. So that means two things are happening simultaneously. One thing is that to check the effect of moving frame of reference on speed of light, various experiments have been performed. Had been performed. And another thing that is happening, people are trying to check the invariance of principles of physics, various principles of physics. And the experiment which people performed, the experiment was Michelson-Morley experiment which people are trying to perform. Michelson-Morley experiment. And this experiment is repeated so many times. It's repeated so many times. And what is the observation of this experiment? That light is always same. Or in other words, we can say that velocity of light or the speed of light is always same in all directions and is independent of relative uniform motion of the observer. So this is one very important observation. Then to validate this or to check this, so Newton's laws are found to be invariant under Galilean transformation. But Maxwell's equation and the consequence of these equation is the constancy of speed of light. This is the consequence of Maxwell equations, constancy of speed of light. But these Maxwell equations are not invariant. Under Galilean transformation. Thus, we have to think more critically, and these Galilean transformations suggest the following alternatives. So these findings suggest following alternatives. So one thing is Galilean transformation was correct. And something wrong. With Maxwell's equations, there is one possibility. And another thing, if this is not true, then there is another possibility that Galilean transformations applied only to Newtonian mechanics. Third thing, that Galilean transformation and Newtonian principle of relativity and Newtonian principle of relativity are supposed to be wrong. And there exists new relativity principles which are valid in mechanics, and electromagnetism. This third point is a very important point. If we will arrive at this point, then that must be worth celebrating. So answer these questions or these suggestions. Two parallel approaches are there. So to answer these questions, two approaches are adopted. So first approach is the idea of new transformation equations. And another thing is the Einstein special theory of relativity. Special theory of relativity. These are the two approaches. So the idea of new transformation equations leads to new transformation equations are known as Lorentz transformations. And these Lorentz transformations based on Michelson-Morley experiment, based on the results of Michelson-Morley experiment, and they started with the modification of Galilean transformation. This is one thing. And then another approach is the Einstein special theory of relativity, and this is based on the properties of Maxwell's equations. And negative results of Lorentz and Einstein, they use the negative results and try to modify the things. So, and the negative results of Michelson-Morley experiment. And based on this study, Einstein suggested postulates of special theory of relativity whereas Lorentz gave new transformation equations. So this is the brief idea about Lorentz transformation and special theory of relativity. And here the very interesting thing which we got, that Maxwell equations are not invariant under Galilean transformation. So in the next lecture I am going to talk about invariance of non-invariance of Galilean transformation, non-invariance of Maxwell equations under Galilean transformation. And then after that I will talk about Lorentz transformation and its consequences. And finally I will talk about special theory of relativity. So thanks for watching this lecture.